Hi everyone, my name is Yuji Zhou from Purdue University, and today I'm going to talk about our system on co-located multi-user Cloud VR. Imagine a scenario where we have 100 or more students in the same classroom, each wearing a VR headset or MR headset. And the instructor wants to stream a large amount of data or the entire virtual environment to each student simultaneously. And can we just use the existing infrastructures like the classroom's Wi-Fi router and the instructor's own laptop to achieve this? So if using the conventional TCP method or conventional unicast method, the total required bandwidth grows significantly and linearly with the number of lines. So the more students you have in the classroom, the larger computational load and network load are put on the server side. And our multicast solution leverages the spatial coherence of the virtual environment because the VR users or MR users that are close to each other in the virtual environment are very likely to require the same data or similar data. So rather than sending individual packets to individual clients, we send the same packet, every packet, to all clients at once using multicast. And here's the architecture of our system. And I'll start from the beginning. We did some pre-processing for our system to save time for packetization and visibility checking. So first of all, we packetize each object into individual packets of 1.4 kilobytes to prevent partial data loss. Each packet can be decoded and rendered immediately upon arrival. They don't need any information from the other packets. And we use a greedy algorithm to choose the vertices and triangles in each packet to maximize the connectivity. We'll also only want to send visible packets. So rather than calculating the visibility information during runtime, we did a pre-processing on the visibility. The first step is to divide the virtual environment into grids of 1 meter by 1 meter. For each grid cell, we pre-compute visibility at the cell corners at a height of 1 meter and 2 meters. So there are in total 4 times 2, 8 corners for each grid cell. And like I said, we only send the visible packets to each client based on their current position. And during runtime, rather than calculating the visibility information, the system just read the files about the visibility information based on the client's position and use those information to schedule the packets to send. And that was the pre-processing part of our system. Now the server knows what to send for each client, and the next question is how to send, how to schedule the packets. Given the position of the individual clients, we not only know what packets they need, but also the order of the packets to send, because we want to give larger priority to those packets that covers more pixels on the user view. And to maintain the fairness among the clients, we did a round-robin order of scheduling. And remember, when the packet is sent, it's not just sent to the individual client that requested, but is sent to everybody through multicasting. And because multicasting is unreliable, we cannot assume the packet has been received by the current client. So we push the packet to the end of the priority queue for a future sending. And there's a special situation for this. When a packet is requested by more than one client and is sent out, it's pushed back on the priority queues of all clients, not just the one that requested. And there are more happening in the loop of the system. And while the clients are receiving the packets from the server, they're also synchronizing with the server about their current positions and what packets they actually have received through a bitmap acknowledgement. And Given their updated positions and received packets from the BBAM acknowledgement, we can update the scheduling we just talked about. The client communicates with the server about every 100 milliseconds, telling the server about their current positions and the bitmap acknowledgement. We set this frequency to 100 milliseconds because we don't want very frequent communications between the server and clients. And as soon as the server hears about the received packets from the client, it removes that packet from the priority queue of that client. Because now we know the server knows the user, the client has received that specific packet. We don't need to schedule for future sending. And we run a user study to evaluate our multicast solution comparing to the conventional TCP solution or conventional unicast solution. And the user study contains 2 sessions, one with 16 users, 16 participants, and one with 7 participants. Here's a user study where the participants were asked to visualize the startup loading and the navigation along the path. And they were asked about, for example, the loading time and rendering quality at the startup and during the navigation. We evaluate our solution with 2 objective metrics. The first metric is the percentage of missing packets over time. So the percentage of packet missed during both initial loading and during the navigation. And as you can see here, our solution significantly reduced the initial loading time. So we're able to drop the time from 50 seconds along one of the paths to just 5 seconds using our method compared to the conventional TCP solution. Another big advantage of our solution is during user navigation. So whenever a packet is requested by a user moving in the virtual environment, that packet is sent to everybody else, even though they don't need it at this moment. So when they started moving in the virtual environment, they're very likely to have received a large number of packets thanks to the Pioneer. So they don't suffer from a large number of missing packets, a large percentage of missing packets when they are navigating in the virtual environment. But on the other hand, for the conventional TCP solution, everyone needs to receive unique packets when they're moving along the path or they're moving in the virtual environment. So everybody suffered from a large percentage of missing packets. When evaluating with the other metric, which is the tracked pixel level depth error, the percentage of incorrect pixels in the user's view, we got similar results. So with our method, only the first participant moving in the virtual environment got a large percentage of image error during the navigation, but all the other users were having a smooth visualization during the navigation. On the other hand, when using the conventional TCP solution, all the users were suffering from a large percentage of image errors. Here is a result demo of using the conventional TCP method. And as you can note here, it took the participants quite some time to load the initial scene. And here we're speeding up because it took so much time. And during the navigation, the individual clients, all of them suffered from incontinuous during the navigation, as you can see here and here. Here's the result of our solution, our multicast solution. As you can see here, the participants were able to see a complete scene in just 5 seconds compared to the conventional TCP solution. And during the navigation, the first participant still suffered from a lot of missing packets during the path. But when the other participant started moving, they still missed a few packets, but a lot less than the first participant, as you can see here.